Hi, everyone. This is Ashley from the EpicEarth podcast. I'm here to let you know that this will be our final episode of EpicEarth. When Brian, Scott, and I started this podcast many years ago, we had no idea what we were doing. It was all a learning curve for us, and it's been a fun journey and a fun experience trying to navigate the podcast world, learning how to edit things, learning how to add in quirky little fun segments. And all I can say is thanks to all of our listeners and to all of the people who interviewed with us and gave us a chance to learn about their science and their research. It's just made this whole process such a blast. Brian and I couldn't be prouder of the product that we've created, and I would say that if you're interested in starting a podcast of your own, just dive right in, jump in the deep end. You'll figure things out along the way, much like we did. We know we're not the perfect podcast, but we had fun nonetheless, and that's what counts. We'd like to say a big thank you to all of our listeners. We can't think of a better episode to send EpicEarth off on. We're interviewing a really good friend of mine, Justin Crevier, who was an undergrad at the time that we interviewed him. He's now doing his PhD at Northern Arizona University in Flagstaff. He's going to do amazing things. And that's what this podcast is all about. It's all about finding those people with a passion to continue in the STEM fields and in science. And he's just going to be the most amazing scientist that I can think of. So without further ado, let's get on to our final episode. Welcome back to our final episode of EpicEarth. EpicEarth is a podcast for those curious about the STEM fields and the awesome, quirky, and fun experiences and research taking place right now. If you enjoy listening to stories like these, hit that like, follow, and subscribe button to listen to our previous 28 episodes. This is episode number 29. The truth is out there. So sit back, relax, and enjoy our final ride as we take you on a journey around this epic Earth.
I found it all so fascinating, just learning all the information.
Nobody told me I couldn't do it, and I loved it.
And now I know how to learn. Like, this is a doable thing.
You know, that's an impact that we can't ignore.
Hey everyone, welcome to another episode of EpicEarth. I'm your host, Ashley Bosa, and with me, as always, I have fabulous Brian Rosenblatt.
Hey, how's it going?
Yeah, so the recording might sound a little bit different this time, and that's because we are actually using the new sound studio in the library, which was pretty much made because of people like us who are crazy and want to do podcasts. So we're super excited to try out this new technology, and hopefully our listeners will like it. So today, before I introduce our awesome guest, I'm actually going to start with some really interesting Earth facts for all of our listeners. Since this is EpicEarth, I thought it might be good for us to just throw in some random facts. So, Brian, did you know that the honey mushroom, or Armilia bulbosa fungus in Oregon, is the largest and oldest living organism in the world? It spans 2,200 acres, and that's about a tenth of the size of the entire Disney World theme park in Florida, for reference, for whoever cares. So
Yeah, I actually did know that. We learned that in elementary school, but...
Oh.
No, I'm just kidding.
I was like, well, my elementary school needs to pick up their trivia. All right. Well,
Never heard of that plant.
No, me either, but apparently Oregon's really good at growing it, so Oregon's just one big fungus, I guess. Also, just to measure up for our listeners, for relative size, if the sun were as tall as a typical front door, so think of your front door to your house, Earth would be the size of a nickel.
Wow.
Yeah. So that's how big our star is, which is pretty impressive. Earth, as we know, is a terrestrial planet, And it's also known as a telluric or rocky planet. And all that simply refers to is a planet that's mostly composed of silicate rocks or metals. So, silicate. And other terrestrial planets in the solar system are Mercury, Venus, and Mars. Do you know what the driest place on Earth is, Brian?
I'd guess like the Mojave Desert or something.
Ooh, close one. It is a desert. It's the Atacama Desert in Chile.
Oh, wow.
It's the driest place on Earth, but despite it being dry to the bone, the desert is actually right next to the biggest body of water on Earth, the Pacific Ocean. And its temps average about 63 degrees Fahrenheit. So even though it's hot, on average it's only 63 degrees Fahrenheit across the year.
Interesting.
I've heard they have some really beautiful like flower blooms as well down there during like the rainy season.
Is that pretty far south in Chile?
I think I don't know. That's a good question. I think it's pretty central.
Okay.
So much for that question because I don't know the answer. And then, did you know that rocks have been known to walk at the racetrack Playa in Death Valley?
I think I have heard that before. They leave this like trail behind it or something.
Yeah, and you can see some really cool photos of this. So in a specific part of Death Valley National Park in California, known as the racetrack Playa, or just the racetrack, rocks have been known to walk on their own. So according to NASA, these ice-encrusted sailing stones, as they're called, retain meltwater from the hills above. And this allows the wind to pick them up and throw them around, apparently. So this phenomenon has been known to leave racetrack imprints on the ground, hence its moniker.
Interesting.
Yeah. So.
How big are those rocks?
Oh, I don't know. Well, I don't know. Maybe our guest knows.
I think they're typically like fist-sized.
Okay.
It's almost like they're hydroplaning on that layer of water as it melts off.
That makes sense. Well, that's a great segue into our guest for this week, who knows a lot about a lot of different stuff. It is with great pleasure that I introduce this individual who is a second-degree seeking undergraduate here at Boise State University, double majoring in geoscience with a geophysics emphasis, and physics with an astrophysics emphasis. So he gets to see both worlds, no pun intended. He's retired from the federal government, where he worked both in the Marine Corps and as an enlisted infantryman, and then an intelligence officer. And he also worked for the U.S. Department of State, where he served as a foreign service officer, so a diplomat, essentially, and we're looking forward to hearing more about that. So it's with great pleasure, once again, to introduce you to Justin Crevier.
Thank you very much, Ashley. It's a pleasure to be here tonight. Certainly good to be indoors since it's cold and rainy out there.
I know. It was quite the walk over to the library.
I drove.
You drove? You hydroplaned? Justin, we'd like to start out with the first question. Tell us a little bit about what makes you you, Justin.
And now, what makes you you?
Well, I'm a lot of things that are maybe a bit unusual in Idaho. I grew up as what's called a third culture kid, which is typically a kid with U.S. parents, but who grows up in various countries overseas. So you're not really an American. You don't like watch the TV shows and eat the food and all that all the other American kids do back in Peoria or whatever. But you're not really an integral part of wherever you're living, which for us was the UK, Switzerland, Egypt, a couple other places here and there. And that gives you, I think, a pretty different perspective on life, especially if your parents try to get you outside of the sort of expat enclave and seeing a little bit more the way people in that country actually live, which is a real eye-opener in a lot of places, especially in Egypt, as you might imagine. Spent my adolescence in what used to be called rather grimly the Fortress. And that's because when we had several million people in the armed forces, we had a network of large military bases all over the world. And I enlisted when I was 17 into the Marine Corps, and got very, very lucky after a few years and got an appointment to the Naval Academy. But that kept me in different military bases, stateside and overseas, which is its own subculture in many ways too, and has slowly, I think, gotten better. But you really see a difference. Most Air Force bases, you can walk off base and be in the middle of a regular city, Sacramento or wherever. Most Marine Corps bases, you're in the southeast somewhere, and it's typically a 10 or 15 minute drive through basically forest until you're at anything resembling any kind of buildings. And that distance, I think, is psychological as well as physical. So spent a lot of my early years in places like that, for better or for worse. Then I got commissioned, then spent a few years doing that. September 11th happened, got recalled after starting grad school for business at the University of Washington. And then I managed to get into the U.S. Department of State and was a diplomat for about 15 years. Wow. And the federal retirement system is Byzantine, but for once things kind of all fell one way, and that was in my favor. And I was able to retire fairly young with a lot of years under my belt and able to kind of do what I wanted, which is studying geophysics and astrophysics.
Yeah.
So,
where were you born, Justin?
New York City. I was born New Year's Eve, 10:40 p.m. So I was almost the New Year's baby for that year. Yeah.
Cool.
He's a city boy.
Yeah, it was an interesting 21st. Went back with some friends and celebrated on Times Square. Yeah.
Nice.
Wow. Nice. Well, you've had such a fascinating sort of life so far.
I've been lucky. Yeah, I've been very lucky.
That's awesome. And so you spent so much time working overseas, going and seeing all these different countries and these different cultures, and really getting to expand on, what's out there. And so what really made you interested in coming back and really studying in geophysics and astrophysics? What was the draw there for you?
Well, a couple different things. As I was getting ready to retire, they actually have us go to a week-long retirement seminar, which is incredibly nice and an incredible privilege for federal employees. And one of the points they made, which sounds really trite, but I think it's very, very germane, is they said, don't retire from something, but retire to something. So don't just kind of get away from it, but make sure you're moving into a new stage of your life, sort of, and not just escaping the old one.
Yeah.
And that kind of reinforced me that I needed to have a plan. And I already kind of knew I was interested in science and STEM. My last tour of duty in the Foreign Service was in the South Caucasus in Azerbaijan, which is a small Muslim state on the Caspian Sea. And I used to take my boys on like Boy Scout hikes and stuff in the mountains there. And I remember seeing this pond. It was just some random pond that probably they washed their cattle in. It was kind of gross and overgrown. And I was thinking, here on Earth, this is just another kind of grubby little place you don't really want to be. But in the universe as a whole, this is a miracle, and that got me thinking about astrobiology. Funny you should mention the Atacama. And perhaps a bit lame for me to say that a movie inspired me, but there is an awesome documentary about the Atacama Desert called Nostalgia for the Light, and it's about all the observatories that have been built there, and literally in the shadows of these observatories are the old death camps that Augustin Pinochet built in the 70s to house all his political enemies and essentially work them to death. And this movie is a documentary examining how these two sort of communities, the scientists who are probing the deep secrets of the universe, and then the mostly wives, widowed wives of all of these political prisoners who spend their day going through the sand trying to find remains to categorize them, how these two communities kind of coexist, and how they've been able to communicate with each other in a way. It's a great documentary, anyway. And that kind of got me pointed back towards what I was interested in. Originally, and this is like probably the weirdest and worst origin story ever, but in 5th grade in Egypt, I caught typhoid. And they couldn't fly me out of the country because I had a communicable deadly disease.
Yeah.
So I spent 5 months in bed, and I missed that first half of 5th grade. But that was the astronomy module. And so they brought me all the books and like left them at the doorstep or whatever they did, slid the dinner under the door,
Yeah.
And I spent a lot of time reading. And I think you get exposed enough to something like that, and it really is becomes something that you like and want to do more of. So typhoid led me to astronomy and planetary science.
Yeah.
Who knew there was a silver lining to typhoid?
Yeah, well, we managed to find one of a sort. So.
That's it. That's really excellent. And then why combine the geophysics with that in terms of why you wanted to study? I mean, because astrophysics, I mean, you're already doing a lot with that in terms of astronomy and stuff. But why the geophysics part of it?
I think there's some very different areas of emphasis. Physics seeks a sort of discrete mathematical solution to almost every problem. Geoscience tends to be a little bit more maybe analog. Mm-hmm. I think the linkage between the two, one of our guest speakers during the pandemic, Elizabeth Tasker, who's an author of several books on planetary formation, works for for JAXA, the Japanese Space Agency now, actually. But she sent Brian Jackson and I a white paper from a few years ago that had been written by the exoplanet community of astronomers. And they were saying, look, we're finding all these cool exoplanets, and we're developing the means of figuring out how far these are relative to their sun. In some cases, how dense are they? So what are the surfaces probably? And every time you read an article that says, this star has a planet that rains diamonds or something, that's because people have meticulously sifted through the data and made all these analyses to figure out how the atmosphere is likely to work. Well, the astronomy community has done all that, but they're self-aware enough and wise enough to realize that they don't understand planetary processes as well. Mm-hmm. And the point they were making in this white paper is we need the geosciences community's expertise. So when we say there are icy moons that that may have some, I'm kind of just making this up as I go along. This is not exact research being done right now. I just want to clarify that. But there are icy moons that have isotopes in the ice that may suggest that there are hydrothermal vents underneath. If something like that were to come up, they need the geoscientists with the expertise who've been studying, seamounts or underwater volcanism or all those kinds of things to be able to step in and say, yes, that's viable, or no, that's not because of this, that, and the other. Yeah. Tectonics, carbon cycling, atmospheric interactions, atmospheric evolution, all those things. There's a huge opportunity for geoscientists, geophysicists to be able to step in and help build our picture. I mean, we're not traveling to these worlds next week, but for better or for worse, this is an area that captures the public imagination. And to capture the public dollars, we need to capture the public imagination. I hate to put it that way, but
it's the truth.
Yeah.
Yeah, and I think you raise a really good point that, how we understand other planets and other systems is by studying stuff here on Earth and understanding our own planet. So that's really cool. And this that now leads us into the next question, which is going to talk a little bit more about your research, because your research also spans both astrophysics and geosciences. So yeah, tell us a little bit about what you're working on, Justin, across both of those disciplines.
Well, I'm very fortunate. I've been able to work with some outstanding mentors in both fields. On the physics side, I've been working on dust devils, doing something called planetary analog studies, and that's where we look at a process that occurs on Earth, and then we try to figure out, to extrapolate, how does that occur on other planets, and how can we model that and better understand it here. It's an inexact science, but it's one that we're building a lot of tools to better work with. And what I do with Brian is we study dust devils on playas. For example, in the Alvord Desert in Oregon or in Smith Creek in Nevada, We go out and we have flown drones into these. We've set up fields of tripod-mounted anemometers for dust devils to blow through, and then we analyze that data, and then we look at the ones that occur on Mars. And Mars has a lot of dust devils. Mars has got a weird atmosphere. The pressure there is less than 1% of Earth's atmosphere. There's very little oxygen. A lot of the oxygen is photodissociated, that is broken apart under sunlight, and is no longer there in any case. But dust devils are actually one of the main ways that the surface of Mars interacts with the atmosphere, that and the huge dust storms that occur. So understanding dust devils is not sort of a niche element of the atmosphere like it could potentially be seen on Earth. It's a fairly large component of how Mars cycles dust through its system.
Yeah.
And one of the key issues with Mars is that dust in many places tends to be extremely fine. And when you start talking electronic equipment, or you start talking, Jane the astronaut taking her helmet off, and there's dust gumming everything up in the gears and the moving parts, that becomes a real issue that we've got to understand.
Mm-hmm.
Second thing I'm looking at is I work with Brittany Brand on the geoscience side. I was very fortunate to receive a Kleinman grant a couple of years ago for volcanology research, and we've been out to Mount St. Helens to the Pumice Plain twice now, and we've been looking at a particular event that occurred during that huge eruption in May 18, 1980. At about 8:30 in the morning, there was the initial blast, which was the shock wave that bounced off the lower atmosphere. People heard it as far as my aunt in Vashon Island off of Puget Sound. And then there were 30 minutes of other events that occurred, but not the main sort of eruption yet. And then at just about 9 o'clock, at 9:02, was the so-called Plinian eruption. And that was when you had a massive column of smoke and ash that ascended skyward tens of kilometers. Plinian's a really odd name. I don't know have you explained that on this podcast before?
We have not, no.
So Pliny the Elder had actually witnessed the Vesuvius eruption. And based on the eruption style he described, that's why they use the word Plinian now, which to me was bizarre. But, we reach back a lot in history to find these resources, I guess. But within that first half hour, there were a series of pyroclastic density currents. And although on a Hollywood volcano, it's usually the lava that kills people, or what we call pyroclastic bombs, the large boulders that sometimes get shot out and always barely miss the hero's Jeep in Jurassic Park or whatever.
They're suburban, by the way.
The suburban. It's actually the pyroclastic density currents that are often the real killers, because these are these superheated jets of gas and dust, and worst of all, microscopic rock shards that will go shooting along, essentially horizontally along the ground, but on a volcano's flanks, you're not horizontal, so they're going downhill, and they're picking up speed. Mm-hmm. And if you're in the wrong place at the wrong time, you're not getting out of the way of this thing, because they're hundreds of degrees centigrade at least. There were some eyewitness accounts and some photographs, though, of what appears to have been a PDC, a pyroclastic density current, that occurred during that first half hour that people survived. That was under several hundred degrees Celsius, because people were hit by it, but they walked away from it. And we've been trying to trace what exactly is this. Is it in fact what we would normally call a pyroclastic density current, or was it perhaps the result of some form of a vent clearing or a conduit clearing episode, where the upwelling force from inside the volcano, from the magma chambers or gas being released, effectively forced older, harder rock, maybe leftover bits of the cryptodome, or what's called hydrothermally altered rock, or even water embedded in the rock, forced that out, causing this explosion that acted essentially like a pyroclastic density current as well. So we're looking at that and trying to figure out what exactly is this, what caused it, what differentiates it, if at all, mineralogically and in terms of what we call grain size distribution from the other events of that first half hour.
I never knew that even happened.
I think a lot of people don't. Like, it's not really widely explained in the literature, right?
One of the big things I'm finding out as a brand new aspiring scientist is I sort of assumed that a lot of things had already been studied in detail. For example, the Mount St. Helens eruption. I mean, it was literally in our backyard. We have all these resources, but it turns out that a lot of things, the blast phase, for example, has not been sort of extensively sampled and analyzed for a number of very good reasons. In particular, it took years for it to cool in some areas, for it to be safe enough for people to walk on. By then, people had moved on, projects had moved on, funding had moved on. There were other, perhaps more compelling at that time, aspects of the eruption that people were studying. So we were going back through the literature saying, can we find samples to compare what we've sampled and sorted? And in many cases, the answer was not really. At best, it's apples and oranges in many cases. And we're finding that even with things like lunar geology, now that we're going back to the moon, hopefully with the Artemis program, there's a lot of general work that was maybe done in the 60s, but hasn't been touched since then. And the instrumentation's evolved by leaps and bounds, whether you're talking volcanology with electron microscopes or analyzing a lot of the lunar samples that were brought back. So there's, in some cases, this sort of second generation of analyzing these now in a maybe different context.
Yeah.
Absolutely. Yeah, I feel like that could be said for pretty much anything. I feel like, you come in to a program and you think, oh, it's all been done before. Even as a grad student, you're like, what? I can't think of a novel idea. That's ridiculous. And then as you go through the literature and you start looking at the problems, you realize actually there's tons of stuff that hasn't been figured out or studied yet, or some technique that somebody hasn't used yet that you're just like, wow, okay, why haven't we used this yet? And I think, especially with technological advances and our accessibility, so now the Perseverance has the drone on it, and it's now taking these drone photos of Mars. That's a whole different technology that can be used and implemented into research. And so it's really cool to see how people are sort of returning to these spots. And even Mount St. Helens, which is one of the most well-studied, volcanic events in the world. And there's still so much to learn from it, which is, we'll never be out of a job, Justin.
Yeah. That's what I was going to say. Your two fields that you're in volcanology, where volcanoes are always going to change. There's always something to study there, or even just looking at the past with new techniques. And then astronomy, infinite. You're set for jobs now.
Yeah, it's a very different world from being a 19-year-old infantry squadron.
Yeah.
I'll tell you that.
Well, I find it fascinating that, you're studying two different problems on two different planetary systems, and yet they overlap so much with grain size distribution. How are things picked up and moved? Granular flows, how does air move? Sand and gravel and boulders around it. It's really fascinating to see the overlap there too. So I'm sure that's been fascinating for you and Brian, your advisor, who, also works closely with the geoscience department here.
Yeah. And I've got to say, I've been the luckiest person on earth to have the two mentors that I have, because I've worked with a lot of people. I've had some great bosses. I've had some maybe less than great bosses, and mentors and so on through my time, and these are two of the very best people I've ever had the good luck to work with.
I'd have to second that too. I mean, I haven't worked with you, but both of them. I took a class with Brittany, a couple of classes with Brittany, and she's a great person. Mm-hmm. She would be a great person. That's your advisor, right?
Yeah.
Okay. And then Brian Jackson's just a great person all around. So yeah.
Yeah, I love how they both are just always so curious. They always want to expand on the things that they're doing, and it's really awesome to see how engaging they are with different communities. I kind of just wanted to drop this in here because Justin actually just shared with me the other day. We were having this discussion about sand and how it gets lifted, and air and velocity and what happens, and he told me this really funny. There's a meme that describes the different levels of physics, and you probably can describe it better than I can. So,
well, if I use the word XKCD, half the people listening will probably know what I'm talking about. It's by the guy who did What If and all of those other related books. And there's a chart, and he just kind of drew it out as a tongue-in-cheek thing, but it says physics in order of difficulty. And starting on the left side, near the origin is Newtonian physics. And then I think it works its way to special relativity, general relativity, and then you get to quantum physics, and then all the way on the end is sand. And if you've worked with particle transport, if you've worked with, nearly infinite multiple body problems, if you've worked with the impact of surface porosity on transport, you know exactly what he's talking about, and it's quite a problem. Yeah.
It is. Yeah. So we need a lot of technology and problem solving for that, for just sand.
Yeah.
Nothing else, just sand. That's really great to hear, Justin. You're an exemplary sort of undergrad in terms of the work that you're doing, and you're planning on going to grad school. And what do you hope to study in grad school?
I've been able to speak with a couple of different professors looking largely at planetary science, ideally the Martian surface. But I've been able to talk with a couple people who are studying asteroids and planetary defense, the DART program, and in one case, origins of life, so astrobiology. So it's a fairly wide-ranging mix. And I think that comes from being relatively open in terms of what I'd like to study and trying to maintain a fairly broad background in terms of research and academic experience.
Yeah.
So.
And are you looking at master's degrees or PhD?
Direct to PhD,
Cool.
largely because I'm, for planetary science, that's kind of typical, kind of like with physics. Mm-hmm. And then B, because I'm getting a little long in the tooth. And if I get a master's, it may be hard to come back and get a PhD.
Yeah.
And there's some fascinating things out there waiting to be studied. So
You know what you want to do too, so it's not like you're still deciding or whatnot.
yeah.
Yeah.
Yeah, that's awesome. Okay, what is the best or most fun thing about what you do, would you say?
I've mentioned it a bit, but I think it's the people you meet. It's you're starting a project, 3 random people you maybe haven't worked with before. They might be 18-year-olds who've never left Idaho. They might be 70-year-old retired researchers from Los Alamos. Typically, there's something in between. But getting to know people, getting to find out a little bit about how they see the world, and kind of being able to understand a bit about that worldview. As a diplomat, you have to do that. Mm-hmm. You're not there. Sometimes they're pounding the table on behalf of the United States, but your real job as a diplomat, especially now that we have Google Translate and the internet, is to provide nuance, to provide insight to decision makers in Washington, to the ambassador, maybe to your local interlocutors. Here's why the United States doesn't see eye to eye with your government on X. And kind of being able to do the same thing and just learn who people are and why they think. And sometimes it's the youngest, most simplest seeming people who have the most fascinating things to teach you, I've found.
You have a personality that feels like you're born to be a diplomat. You're really good at communicating. You speak really well, and you're just a people person. Everyone likes you. Have you always felt like you've been like that? Like, where did your communication skills come from, I guess, is the bulk of my question.
When I was a 24-year-old midshipman at the Naval Academy, I was put in charge of my company, which is like a peer leadership thing. So you're in charge of 120 people kind of in your cohort or whatever. And I went up to the Marine officer who ran our company as this major, and I said, "Sir, I'm not doing all that well academically. I'm in good shape, but I'm not like a varsity athlete. I mean, I was a bit too old and creaky. I'm not like a standout, and here I am with all these incredible people. Why did you put me in charge? Not that I mind, I'm happy, but..." And he said, "Well, a lot of different people have told me that Justin is the only person who's still welcome, like in every little group by our senior year. The jocks, the kind of the people who want to go into nuclear power, maybe the engineers. You're one of the very, very few people who can be welcome in all these circles and still communicate." So I'm not sure. I think it takes a certain amount of sort of mental flexibility, maybe.
Yeah.
And sometimes you feel like you don't have the absolute conviction about things that other people do. But growing up overseas, if you're not hiding behind the walls of your, of your expat home, it's very difficult to not see the world in many parts of the world in shades of gray.
Yeah. Yeah. Like that's such a valuable childhood experience, just being well traveled like that, and yeah.
Also, just like a natural born leader. You
Yeah.
know, you don't necessarily command attention, but you know how to lead people in a way which is just very inclusive and very, I don't know, mild mannered, and it's kind of nice.
Yeah.
I think all of us in this room are kind of like that in a way. It's just. Some people have it. Some people are told they have it, and they don't. Some people believe they have it, and they don't. But yeah.
I know exactly what you mean. Yeah.
So Justin, if you could describe your work using an analogy, what would it be?
I had to think a bit about this because to me there was a really, really obvious one. And in many ways, being a scientist is like being an intelligence officer. And it's because you're trying to find the answers to questions. And to an external observer, or maybe to the person that you're doing this work for, your commanding officer, for example, in the Marine Corps, things seem very clear. But within your sort of scope, what you really need to do is to narrow things down. You need to figure out what are the fundamental questions I'm really trying to answer. What is the data I need to answer those questions? Not only that, but what is the data that will be available to answer those questions? And then once I have that, what are the, for the lack of a better term, what are the usable products that I can create with that? Can I provide sort of finished intelligence or an assessment, or can I provide a research study that's of use to people? Or will I have dug in so much on some minutia that it may not be of much use to anybody? And the results you get may not always match what you expected or what you hoped for. And if I could use one analogy maybe, my very first job as a diplomat was in West Africa. And I was sort of the guy on the ground investigating and leading the U.S. government's effort into combating slavery. And I will guarantee you that everybody involved in that effort, from people back in the States I was reporting to my colleagues on the ground, we had one thing in mind, and that was to wipe this from the earth. And I think anybody listening to this would feel the exact same. But the problem was, we did not understand the scope of the problem. We didn't understand the nature of the problem. And we needed to do that before we could begin to find a solution. And before I sound like I'm justifying an abhorrent practice, what I mean by that is this was not the slavery that we, to our shame, practiced in the United States. People were not being bought and sold. People were not being exploited in the same way. But what it took us a while to find was that people were being raised in a condition of economic dependence, complete ignorance, and servitude. Once we had determined that, and we were already putting pressure on the government to enforce, on the local government, to enforce the laws that would free people and would make this such a criminal practice that it would disappear. The other issue we had to look at was, if these slaves are freed, where are they going to go and what's going to happen to them? So before we could really start tightening the screws to make enforcement stronger, which has to be by the local government, we can't parachute in the 82nd Airborne to make this work. We had to get other projects requested and luckily funded by the U.S. government, by the UN, and so on, so that when people were freed from this condition of slavery, they would have a future to walk into. Unemployment in this country was already horrendous, and you're talking releasing people in their 20s and 30s with no job skills, without even the ability to count money, into a job market that didn't want them. All the goodwill in the world doesn't give them a future. So we needed to have that that gateway to a future in place for them before they started seeing real freedom. And if it hurts to hear that, imagine being the one who has to explain that, that we're not forcing this as much as we would like because we don't want to just release people into as bad of as an existence of before. So anyway, that's not exactly the same as scientific research, but it is about asking the right questions, finding what solutions are available, and turning those solutions into actionable results.
Yeah. And yeah, what I'm mostly hearing from that is like you need to think like a scientist while you're being a diplomat. And actually the last person that we just interviewed, one of her whole shtick was like she does everything like a scientist. She always thinks like a scientist, and that's just her mythology to get through life, essentially. So it's cool to hear a similar theme from you. Yeah.
I think it's a rational approach in knowing your limits. You know,
definitely.
Excellent. Yeah, that's a really good answer.
Yeah.
So Justin, moving on a little bit from that, do you have any fun stories from the field that you could talk to us about?
I think a couple. I think one of the coolest experiences for me, I'd never seen elk in the wild before, but Aaron Marshall, who's a PhD graduate from Boise State, and I went back out to Mount St. Helens this past August. And the Pumice Plain is a pretty barren place, even now in terms of people. And you'd see maybe one person a day if you were there for 4 or 5 days. We went off trail, but we went so far off trail that instead of seeing the herds of elk in the distance, we were seeing the herds of elk between us and the trail. And the trail is just a couple of cairns of stones here and there and footprints. So we knew we were really out of it then. And that was a really interesting perspective for me. I think the other one, though, is the first time we went out there was with a gentleman by the name of Bill, who'd been at Mount St. Helens during the original eruption, or immediately after, like weeks afterward. And he had not been back since 1980. And when we stepped through, there's kind of a brushy area that you walk out and you first sort of see the whole plain. And he just stopped and he was in awe because the last time he had been there, it was the surface of the moon. It was gray dust, gray rock, nothing else. And now so much of it has grown back. You've got probably 2 layers of flowers, of shrubbery, of bushes, and the fauna are coming back. The elks I'd mentioned aren't all that visible, but it blew his mind that things could change so much in 40 years.
Yeah.
And I thought that says a lot about sort of what life will do to go on. But
Was that Bill from the Soils?
no, that's a gentleman by the name of Bill Criswell, who retired from Los Alamos and had been doing some initial research into this pyroclastic density current that we were investigating.
Cool.
So yeah.
Cool.
Yeah, that's a really interesting, fun fact to see someone who was actually there at the or just after the 1980 eruption, and then come back and see just life comes back.
Yeah.
Yeah. Great. Okay, I'm gonna get into your first serious question.
Uh-oh. You break my books out. Yeah.
So I'm gonna ask you to solve or how would you solve a scientific problem if you were from the Einstein Cross? And I'm going to ask you what that is, and then I'm going to ask you what your scientific problem would be.
All right. Well, there's several Einstein Crosses, but I'll just call it the Einstein Cross for simplicity's sake. But it's not actually a physical thing. It's kind of an illusion, but it's an illusion that proves special relativity, which I think is really, really cool. And it's this idea that the idea behind special relativity is essentially that mass bends space-time. And the Einstein Cross is the result of a gravitational lens. And if you imagine almost a giant glass lens of a telescope, but the size of a galaxy, and if that lens is perpendicular to us, then it will bend light from objects farther behind it. And what we will see is instead of that lensing galaxy, we'll see something that may be megaparsecs, a long, long way behind it. And instead of one of those, we'll see 4 of them. And it's not a perfect quadrant. They're a bit distorted because these lenses are never quite perfect. But these lenses, in addition to being visual proof of special relativity, are almost certainly one of the key clues that we have to the existence of dark matter. And dark matter in a nutshell, in a very thin nutshell, is this idea that the larger you scale the objects that we can see in deep space, other galaxies, galaxy clusters, and so on, the less they obey the laws of fundamental physics that we see them in terms of momentum and velocity. A spiral galaxy's arms will turn at a rate that's completely not what we would calculate using the physics that we know. And the only way that we can find to adequately and consistently explain this is that there's a lot more matter out there and therefore generating a lot more gravitational pull than we can see or perceive using the spectrum that's available to us. And that's why it's called dark matter. And it's not some sinister, Lovecraftian presence outside the stars, or there's dark energy as well, and there are some refinements between which is which. But when you look at what we can mathematically show, the physical matter that we can see is actually only a tiny fraction of what must be out there to create the movement and the other interactions that we are measuring. So on the Einstein Cross, I would take every instrument known to man, plus some, if they're anywhere available, and try to figure out what this dark matter is.
Huh.
Dark matter is out there, people.
There are some awesome, awesome NASA posters in this sort of retro tourism style on dark matter, on take the family on a ski trip to the rings of Saturn, all that kind of thing. There's even a collection of Halloween ones with zombie stars and stellar graveyards. They're amazing. But if you're looking for something to decorate your dorm room with or your cubicle at work, NASA will let you print them off for free, and they're great.
Nice.
Brian knows what I'm referring to, I think. Yeah.
Oh, yeah. Well, now my cubicle's just going to be all this NASA stuff.
Let me divulge into your question farther. Is an Einstein Cross an ideal location to study dark matter? Does it matter?
I'm going to give you a typical non-answer, which I learned to do as a diplomat as well. It depends.
Yeah.
Very diplomatic.
The cornerstone words of the Foreign Service. It depends. Yeah. But we don't know enough yet to know whether sort of if I could physically stand in the middle of this illusionary construct, would I be able to sample something, or would it be somewhere else? It might be like standing at the end of a rainbow.
That's exactly what I was thinking.
Exactly. Yeah, there may be no pot of gold, or I could be blinded by the light. Who knows?
Yeah.
Great song, by the way. I still love that one.
Yeah.
Okay. Well, I'm gonna sort of have a related question to relativity. So which has a greater gravitational pull on me? Is it the sun or the mass of all the spiders on Earth?
Which one would repel you more quickly? I would guess would be all the spiders, because isn't there supposed to be like a spider within 9 feet of you at all times or something?
It's closer than that, I think.
Yeah, I bet it would. Yeah. I think spiders would make us move more quickly, but the sun with all its mass definitely, technically, scientifically, less dramatically maybe, has more of a pull.
Great answer. Okay, I'm going to ask you another question here. This is kind of silly. And by the way, all these questions are from Randall Munro's sort of website, the XKCD.
Oh.
So if anyone's interested in reading some of the answers that he's put up there, it's pretty funny stuff.
Cool.
It is.
So imagine that, this is kind of morbid, but imagine, I died in a volcanic eruption. And because that would be the superhero way to go. And I wanted to put my remains in some sort of capsule and be shot out into space. What would happen to my body in orbit over the course of years or decades or centuries?
Are you already ash? Are you already tephra? Or...
I mean, I'm still, maybe I got burned a little bit. Like, if I were alive, I need, like, a skin graft, but I'm pretty much still, like, you would know it's me.
And you're just, like, in a loose capsule. It's not airtight or anything, right? Or
let's just say a coffin.
Okay, I'm just trying to narrow down the parameters here a little bit.
You need to.
Yeah. I would guess that depending on sort of how high up in the atmosphere you were, or if you were sort of outside of most of the atmosphere that we interact with, you would, well, let's stay with the morbidity. You would probably slowly decompose into a sort of a frozen slurry as the wood splintered, and eventually there'd be this sort of organic cloud of material that would slowly spread through the atmosphere, and you become part of that gigantic cloud of debris that we have to watch out for every time we launch something.
You're welcome. You're welcome. I like to disrupt science as well.
Yeah, you'd be like space roadkill.
Yeah, that's
nice. Great. Well, for anyone who's thinking of that method.
I didn't read the book. I just made that up. So.
Yeah, well, no, that's great. I think that's a great answer. You can go find Randall's answer to that if you are interested.
Hopefully he's not hanging his head in shame somewhere right now.
So as part of our interview, we like to sort of challenge you on trying to describe your research to 3 different sets of people, and I'll let you choose which portion you want to describe, either Mars dust devils or Mount St. Helens pumice plain phenomenon.
Okay.
So I'm going to just have you. This is sort of your elevator pitch, because you're going to grad school. You're going to have to do this like 6 billion times. So we'll give you some practice here. Describe your research to the following. So the first set of people I'm going to have you describe your research to is an elementary class of maybe 4th and 5th graders. How would you describe your research to them?
5th grader.
I had to write these down because that's probably the hardest level to communicate with when we're so used to using words to parse all our meanings. But I would say for the first one, I look at how volcanoes start to erupt. And secondly, for the dust devil research, I would say I also look at how the wind works on Mars.
You got one for both.
Yeah,
that one I kind of had to make sure I wrote something out. Yeah,
nailed it. Yeah, that's about their attention span, so I think you you got it. Okay, the next set of people would be like an undergraduate student outside of your area of expertise. So someone maybe in business or, communications, maybe someone who's not familiar with the physics or geoscience side.
Undergrad.
So I'll do volcanology there. I would say that we have a pretty good idea of the sequence that leads volcanoes to erupt, and then sort of in that moment, how and when they start to erupt and enter the different phases that take the eruption from sort of usually small tremors, perhaps a few days prior, to the actual main eruption where stuff is belching out everywhere, and we're disrupting air travel and everything else. Looking at that sequence, though, we're parsing it down into each different step and trying to understand each one of those and what are the critical junctures in that step that we have to understand. Because we cannot, one of the key issues of managing crises is you've got to be able to tell people when they should leave and when they have to leave. And if you keep telling people when they should leave and it turns out to be unnecessary, then they won't leave when they have to leave. So the better we can build our case for when people should leave, the more we can protect. And that's an essential part of what I'm studying with these early steps of the Mount St. Helens eruption.
Perfect.
Yeah.
Do you want to do my 3-minute thesis for me?
Are you doing the 3-minute thesis?
I am.
Yeah,
Oh,
let's
I'm
go.
convinced
Great.
by Brian Rosenblatt.
Let's
convinced
go.
me. We'll see. I'm still convincing myself that I should do it. Okay, and the last set of people would be like a professional at a conference. You've had some practice with this, so.
Expert.
Okay, well, there I'll talk a bit about dust devils, and I would say that we've been using a variety of UAS-based, anemometer-based, and other in situ methods to collect data on grain transport, on saltation, on changes in temperature and pressure, on potentially changes in the electromagnetic fields that are caused by vortex activity that we normally characterize as dust devils. And we're using those as analogs to better understand how and why the dust cycle on Mars works, how and why the dust budget functions, particularly in years when there's not a major regional or planet-enveloping dust storm that completely changes the surface morphology, at least of the first few inches or first few centimeters in SI terms.
Yep.
And that's really the focus of what we're looking at and projecting that into better understanding how planetary atmospheres in general work.
Now you got me thinking, are there changes in the magnetic field within those vortexes?
There appear to be some very minor ones, but it's a difficult thing to measure.
Yeah.
And logically, if you've got dust and sand interacting at high speed, sort of high velocities locally, generating that friction, and there's vortex activity going on and changes in pressure, then that strongly suggests that there are some changes in electromagnetic field. Are they enough to matter? We don't know yet.
Yeah.
But when you project that, when you extrapolate that from a dust devil on Earth that may be 20, 30 meters high to some of the ones that we've seen on Mars that in some cases are 2 kilometers high, you might see some real scaling effects there.
Yeah, definitely. Plus the different material, more dry, and who knows what else. But
exactly, yeah. And you've got, in general, Mars has a much thinner mantle, and therefore much more of the iron and nickel has made its way to the surface, which means in turn a lot of the magma that has come out is enriched in iron compared to what we get on Earth, which is more enriched in silica. What that means is that as this stuff is weathered over time and turned to dust, in some cases very fine particles, you've got a lot more, presumably, ferromagnetic stuff, so more electromagnetically active, at least potentially.
Yeah.
We don't know enough to definitively say that, but based on everything we know here, that would be a reasonable inference to make.
Totally.
So
yeah. Crazy.
I know.
Maybe we'll charge our cars with dust devils on Mars. Who knows?
Yeah.
Siphon them down here.
Yeah.
Or from Alamosa, from fire devils or whatever.
Oh, brother. Yeah.
So just as an inside, well, not really inside joke, but so from where I live, where I grew up, there are the Great Sand Dunes, which is this phenomenal, dune park. And Justin was actually there last summer doing some research with NASA. Who were you doing?
Yeah, it was the Planetary Dunes Conference. Yeah.
Wow.
And this park has like a tiny clump of trees in one corner.
Yeah.
And we went there, sunny day, and inevitably all these scientists are there looking at dunes. And about an hour later, it's overcast. We're still out there setting up tripods, taking readings, doing our thing. And then a storm starts. And then we get a lightning storm. And then this park ranger comes running up and telling us there's a fire, you need to leave. So we're kind of walking out to the cars, and they're like, no, you need to leave now. And when we got out in our vehicles, we realized why. There was probably the entire Alamosa Fire Department pulled up, and there was this, I think the term for it is an ash devil. It was like I would call it a dust devil, but it was more kind of like a mini tornado in that it was fast and strong and violent, and it was consuming all of this like small wooded area at an alarming rate. And if we had seen it at night, we would have seen it glowing.
Yeah.
And frankly, I could understand if I were standing on the plains, 1,000 years ago, how terrifying this thing would be. Because you look at it, and if this thing is headed your way, you're done.
Yeah.
So, yeah, and it chased us off. We have good footage of it still.
Yeah, I was going to say, all the
Really?
scientists in the vans are
Oh, yeah.
filming
Oh,
it.
yeah.
Oh, wow. I have to see some of that.
Oh, that's really funny. Anyway, so that was a bit of a tangent, but I thought I'd throw that in
Oh,
there.
it was cool.
All right. Well, Justin, we're going to finish up with a couple more questions. One more serious question for you. If you could be any superhero, what would you be? What would be your superpower?
Oh, wow.
Hardest question of the night
Yeah.
so far.
Brain power.
Yeah, I don't know. I would have to revert to one of those people who's like the night sky or something passive. I don't know much about superheroes except from watching things with my kids.
Yeah.
But I think it wouldn't be so much running around beating up the bad guys as much as it would be sort of
I'm the night
learning
sky.
more and knowing more. Yeah, well, there's in a lot of the old theologies. Having grown up in Egypt, we spent a fair amount of time in these different tombs and pyramids and stuff, and you get a better idea of how they saw the world. And a lot of just the backdrop was a god or a goddess of some kind. And it was pretty cool. They weren't so much doing stuff as they were creating the environment in some ways, in a lot of cases.
So
Maybe
you
I'd be
create
something
dust
like
devils
yeah, there we go. The god of dust devils. Yeah.
on Mars.
Yeah, it would be cool. Actually, I think one of the things in the Middle East, and I can't say this with complete authority, is the idea of dust devils may have helped to create the concept of jinns, and DJINN, not the beverage. And in some forms of Islam, jinns are sort of seen as this intermediate being between Allah, between God and man, sort of a higher than man but lower than God. And the presence of dust devils may have fed into this concept, which I think is really interesting. So maybe I'd be a jinn.
There you
I don't
go.
know. There we go.
Solved it.
Yep.
Have you ever read or watched The Watchmen? It's just the DC comic.
I have. That was really cool.
Yeah.
I like that.
The comic is just great to read. But do you remember Dr. Manhattan?
Absolutely. How
That's
could
what I
you
was
forget him?
picturing
Yeah.
when you were talking about your power. So
Yeah, he got caught in a chamber, right? He
yeah,
was
I don't remember what it was.
Yeah.
Some kind of particle accelerating thing or something, and
Yeah.
tore him to shreds. And like half of the time, he's just like trying to collect himself so he can like become a physical being again in the world or something.
Shoveling himself up. He's
Yeah.
like, where am I?
He's just like spontaneously like appearing in an area, and he's like screaming, like trying to pull his body together, and then he just vanishes again. But by the end, he figures his power out, and he's just like this omnipotent being that can
my
do
gosh.
whatever he wants. And he ends up just like mostly observing. He's existing at all times, at all places at once, and he's decides to keep hands off and just observe basically for the most part. So
There you go. That's
Yeah.
Justin to a T.
yeah.
On that topic, though, it's fascinating in terms of superheroes that we went from Watchmen, which, if I remember right, makes a reference to somebody named Ozymandias. And look on my works, ye mighty in despair. You're supposed to kind of know who that quote came from. And there are all these other literary references, at least in sort of the book, the graphic novel.
Yeah.
So we've gone from there, and in the span of 20 years, now we're at The Boys.
Yeah.
Which, if you've watched it, it does not have a whole lot of literary references, at least to anything that you'd want your kids reading. But it's a very interesting transition, I would say.
Yeah. Absolutely.
Comment on society. Who knows? Justin, I'm just going to finish up with this last question. I just want to also highlight all your work that you've done with me, which has been amazing. Again, you're an exemplary undergraduate. We love having you around. Brian's mentioned how nice and how amicable you are and how, everyone loves to be around Justin.
Yeah.
So You work with me on inclusive leadership within the department, and I just love having conversations with you because your brain is just like an encyclopedia, and it's fun to dive into conversations with you. So what I would like for you to sort of end on is, what advice would you give to maybe not even just undergraduates, but to maybe high schoolers or middle schoolers who are thinking about a career in STEM?
Well, I'll come up with a couple of things. I think the biggest barrier to entry, especially into physics and astronomy, for people who are interested, is math. And I would say the way to deal with that is master the math, treat it as just something you've got to do, but you've got to be on top of the math to be able to sort of play in this league, unfortunately. And it's something that you've just kind of got to sit down and work your way through. And I would submit that the process of mastering math, especially if you don't like it, will teach you a lot of things about yourself and about how you learn complex subjects that will make you a better student in the things that you do want to learn about. So number one would be master the math. I would say number two, for a career, you probably want to get at least a secondary specialty in something that's not maybe all that mainstream. And by that I mean maybe coding or something along those lines. There are a lot of very talented people who want to work in these fields and who are good at, a lot of people are good at a lot of the same things. Find something that's maybe a little bit off the beaten path that there's a need for, and make yourself very good at that. And I think that the opportunities will always be there. I would also say apply for everything. And I'm saying that as someone who literally barely graduated high school and then wound up in a very selective college a few years later, perhaps by taking the most difficult and roundabout method, but still. I'm an odd demographic as a much older person here, but I've applied for a whole lot of things and I've been successful in a surprisingly large number of them. And it's not because I'm great by any means. It's because what I find out after I've been accepted is that in many cases the applicant pool was much smaller than I thought. And in applying for those first few things, you're writing personal statements and you're climbing that difficulty curve. When you apply for other things that may require longer statements or shorter statements, you've already got a lot of the work done.
Yeah.
I'm writing statements of intent for grad schools now or for the GRFP that contain points that I made 4 years ago when I was applying for some of the early programs that I was looking at for summer or within Boise State. So you build on your previous work, kind of like a scientist.
Yeah.
And finally, I would say use every non-classroom opportunity you can find. Join clubs, make friends, get involved in outreach, because you're going to find your work not by getting a 4.0, that doesn't hurt, but you're going to find the work that you want to do, the people you want to work with, the field you want to be in, by talking to other people, by hearing what they have to say, by saying, ooh, that's not what I thought this particular discipline was. I don't think I'd like to do that after all. Maybe I'm happier over here. Mm-hmm. So hopefully those are helpful to people.
That's phenomenal advice, actually. I agree with every single one of those points. And kind of just stepping back to the math as well, this is something Brian and I have talked about way early on in this podcast, but when you're doing something that you love, the math just comes naturally. When you apply it to the things that you really want to do, I'm not a math person. I'm definitely a right-brained person. I write more than I can calculate math. But I excelled in math with volcanology and geology because I was so interested in it that now I'm applying that math and being able to use it is, yes, you'll go through grade school and you'll go through some math classes where you're just like, ugh, why? Why am I learning this? Mm-hmm. But it will help immensely, especially later on when you start applying that to whatever field you decide to go in. So excellent answers. Justin, this has been an absolute pleasure. You are such a awesome person, and you're going to do amazing things. And we are so honored to have you on our podcast. And if there's anyone out there who has not talked to Justin, they should, because he's great. But also, if you'd like any advice on, double majoring or what, astrophysics or geoscience looks like, feel free to reach out to us. And thank you again, Justin.
Thank you for having me on. It was a pleasure to be here, and always awesome to be able to discuss issues like this.
Yeah.
So, thank you.
We love it.
Very happy to have you.
Thanks, everyone, and we'll see you next time on Epic Earth.
Have an epic day. Well, that was an epic conversation.
We'd like to thank all of our listeners.
Tune in next time for another Epic Earth podcast.